hurry up then. Okay, we are in chapter 16. We're going to approximate normal data. We're going to do curves. We're going to standardize the normal data, but we're not going to talk about the 69, 95, 97.7 rule until next time. All right, so we have a frequency table that has heights of NBA players. Looks like our team at Iowa Western. One 7.76 guy, and the rest in the sevens for the starting lineup. And we see the normal heights of normal people, and we see the height of the NBA players, and we see that they win. I think that's what that shows. We can see that the bar graph fits roughly the pattern but it's screwed off center and in a shape of a curve that is not quite symmetric. Isn't that nice? An idealized bell-shaped curve of the data would be in red. So I'd be red, and I'd hit some mean, and I'd half the guys on one side, half the guys on the other side, and that would be a normal curve. NBA players are not normal. It's not a quirk of nature that NBA players aren't normal. But if I have a big enough data size, 1,500,000 people, then I look at their SAT scores, that should be a normalized curve. So here we are sitting here with SAT scores, and sure enough, that more or less fits a standard normalized curve for SAT math scores. And oh, this is the low end, and that's who put the high number on the left? The orange bell traces the curves, the red blah, 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 blah. Okay. Unlike the curve in figure 6, whatever it was, the orange and the red curves are very close. Yes, I agree, they are. Two very different set of data and two very different outcomes. But both of them approximate a normal distribution, but we haven't told you what a normal distribution is. That doesn't happen until halfway through the chapter. Oh, normal means a perfect bell-shaped curve is what that means. Absolutely perfect fit. Normal means approximately half the, let's see, normal data, normalized mathematically, blah, blah, blah. Okay, oh, did I miss something? There may have been some improper use of the English language there. No, I didn't. I was just, my trifocals got in the way. The tighter the fit between the normal distribution and the normal curve, the better analysis we can draw from the conclusions. So if I pick enough data, I should be all set. As usual, we see that the letter N represents the data set, number of data set. The bigger that data set, the better. The smaller it is, that won't be cool. Uh-oh, now we have to start all over.
No.
Okay, a little pause. So now we have midterm scores on the statistics test, and we see that data is totally out of hand. But we can make up a frequency table of the data, and then we can go in and do something with the data. What are we going to do? Come on, make up. There we go. Now we have a chart of the data. And a normal distribution would probably look something like this. So it's not totally normal, and we have one really smart person over here only got one right. You know how really difficult it is to just get one right. Have you ever tried that on a test?
No.
No, it's really difficult to do, because even if you guessed all A's, you get more right than that. And then there's somebody over here who tried to miss more than one but failed. Bar graphs are easy to read, they're easy to see. Data size is 75 for this particular thing. Are we going to put a normal thing on this guy? No, we're not. All right. So now we have 12% of the 75 students did something. So it looks like we're trying to do something. Pictographs, there we go, that's better. We got to take the same data into a pictograph and use frowns and smiley faces. So that looks good. This looks What is this?
I was gonna say, I think
Are we in the
14.
wrong chapter?
Yeah, we already went
Are
over
we
it.
did? Well, who did that? No, right there it says 16, section 1.
Yeah.
It does. Go back to the slide.
Right there, right on top. 16,
I
section
know,
1.
But it was using.
Yeah, but that first slide even, that's what it says.
I know.
And then the other
All right,
side.
we're going to open up. Obviously, the author went and mixed and matched his slides here for some reason. All right, well, that was good. I'm glad we figured that out. Normal curves and normal distributions. Well, thank you very much. Some German guy, Carl, decided that he's going to have normal curves and Gaussian curves, and they're going to be so much better. So mathematically speaking, whenever they undo blah 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 summary, normal associated normal distributions, the facts are greatly later. Okay, we're going to do that later. All right. A normal curve is symmetric. So that means half the stuff is on one side of the center line, half is the other. Both halves look identical. So that would be nice. So here we are. The mean, the mean and the medium are the same guy. Now in our other data sets that was never the case, right? The median was one number and the mean was something else. But if I have a normal curve, the mean and the median are exactly the same spot. And if I look at the light blue section and I flop it over on the dark blue section, they're going to cover each other up. 50% of the data are on either side. What if I have an odd number? I mean, somebody has to be on the top, right? If the distribution is approximately normal, then the median and the mean are going to be approximately equal. Isn't that lovely? I think these guys just make this up. I really do. Standard deviation, the Greek letter sigma. If I have a normal distribution, there's going to be an easy way to describe how the curve looks in relationship to that normal distribution, which won't happen until Thursday. If I take the first derivative of a function, I can figure out whether or not I have a maximum or a minimum. If I take the second derivative of a function, I can tell the point where a function changes from concave up to concave down. So the standard deviation occurs on the bell curve at that point, where I change from concave down on one part of the curve to concave up on the other part of the curve. So if this were a calculus-based type class, we could get an equation of the curve, we could find a second derivative of it, and we could find that point and know where the standard deviation was. But that would be so boring that it would be pathetic. Okay, but where the wire is bent, that spot on the wire is where the standard deviation is. So I'm concave up, I'm concave down. At that spot, that's where one standard deviation is, and we call that point P, the inflection point. And it won't be until you get to Calculus 1 that you'll hear inflection point ever again in your entire life. Won't that be lovely? So I move my hands down the wire and I find where it changes, and that's where I'm going to go and call it. So that P point, that inflection point, is going to be one standard deviation away from the mean. And on either side, it could be on the other side too. In a normal distribution, the standard deviation are equal distance on both sides with the symmetry line. Quartiles. In chapter 14, we figured out a way to figure out quartiles. In this chapter, all we have to do is memorize that the quartiles are at 0.67 of the, we're using 0.675 of the standard deviation. We can find the first quartile or the third quartile, and I'm sure we'll have problems. We'll have to do that. So the third quartile, the mean, or the median, because it's the same thing, plus 0.675, whatever the standard deviation is, and the first quartile, the mean or the median, minus 0.675 times the standard deviation. So I've got 1, 2, 3 things, 4 things. So I'm going to have to know at least 2 of them in order to solve the problem. So now we have a medium at 515, a standard deviation of 114, and we want to know something about this set. And the medium and the mean are the same. 115, that applies. We have half the number going one way and half the number is going that way. The first quartile, 115 minus 0.675 times the standard deviation. First quartile, the same thing. How come? Why? Why? Why isn't that a 2? Why isn't this a 3? The third quartile, Q1. Isn't that brilliant? Way to go, author. Who proofed this slide? I guess I should. Do I have control of this slide? Can I change it? I don't know. I should be able to edit this, right? I should be able to put something there. Oh, that'd be too much time. Maybe we should work a problem. Are we on track still for getting out of here at a reasonable time? Almost. Okay. So problem number 1. Has to be pathetically easy. Consider the normal distribution. Find the median. Okay, so the mean is 83 pounds because that's the center. Find the medium. The medium is equal to the mean, 83 pounds. Find the standard deviation. The standard deviation is the mean plus 0.675 times, no. Write down the answer, it's given to you. 90 pounds. No, 90 minus 83, the standard deviation 7 pounds. Okay. Going too fast. Is that the problem? 7 pounds. Oh, well, we did 1. Problem number 7. Consider a normal distribution. Okay, so Q1 is at 432.5. And Q3 is at 567.5. Find the mean. If I could spell mean. There, is that better? Nah, I don't think so. I think we ought to get a little bit off of there. There, that's better. Well, the mean's got to be between those two, right? Like in the middle. So if I go 432.5 plus 567.5 and I divide by 2 and I get 500, then that would be the mean. Do I get 500? I most certainly do. Find the standard deviation rounded to the nearest point. Okay, so Q1 is equal to mu minus standard deviation times 0.7565.
675.
675? Okay, there we go. I knew I'd remember it, or one of you would remember it. Okay, so I know that this is 432.5. I know that this guy is 500. I know that my standard deviation is my standard deviation, 0.675. Okay, 500 goes on the other side. I get minus 67.5. And then I'm going to divide that by minus 0.675. I am. Is that what I'm going to do? I'll put that over there. And I'm going to divide by that. Yeah, I guess that's what I'm going to do. At least I'm going to get a positive number. Wait a minute. That's 100. So my standard deviation is 100. Is it not 100? Yeah, that's 100, yeah. Right? Well, maybe I'll put it in my calculator. 67.5 divided by 0.675. Oh, 100, yes. All right, lucky guess. 7.
I just know two negatives equal positive.
Yes, that's right. I'm dividing by two negatives, so that makes it positive. I agree. What? Got a question?
Isn't the standard deviation negative though?
No.
Since there's a minus there?
No.
No?
Mm-mm.
Okay.
Nope, standard deviation is never minus. Let me think. Even if the data set was only negative numbers, the standard deviation would still have to be positive. Now, why is that? Well, the standard deviation is the mean minus the value squared, the summation of it, divided by n, square root, right? The square root of any number has to be positive, right? Well, it doesn't have to be. I could have imaginary numbers, but we're not going to deal with imaginary numbers, so therefore that has to be positive. So if I look at the square root curve, it looks like that, right? And at 0, I pass through. Well, that's not the square root curve. That's the e to the x curve. I think I'm demented or something. Anyway, check my word for it. You can't have square root of something and get a negative number out of it. 9. We're doing so well. Estimate the value of the standard deviation rounded to the nearest tenth of an inch of a normal distribution. Mu is 81.2 and Q3 is 94.7. Didn't we just do this? 94.7 equals mu 81.2 plus 0.675. I knew I'd remember that number. Standard deviation. That goes over here, and I got 3.5 divided by 0.675 is equal to my standard deviation. 0.3, and I can't do that in my head. Bummer. I bet you I can. No, I can't. Yes, I can. No, I can't. 75. 5 point something. Number 9. Rounded to the nearest tenth. 5.2. What's the units out of standard deviation? That's right. There are no units on a standard deviation. Okay, just one of those trick questions. No, I had nothing better to do, right? So I asked something like that. 17. Okay, we can't do 17 yet. On to section 3. Standardizing normal data. Okay, so the issue is we got this data spread all over the place. We're going to standardize it. We're going to make it do something weird. All right, good enough? We have seen normal curves, but they don't all look alike. So we're going to have standardized normal curves so that they all look alike. And we're going to use a thing called a z-value. So we're going to take our individual values of x, and we're going to change them to z-values, and then we're going to graph the z-values and have a standardized normal curve. All right, so here we are. Consider this data. We have points A, B, and C, and there's mu, and we're a half a standard deviation and a whole standard deviation, and minus 2.34 standard deviations that way. So that's the data set we're dealing with, and we're going to, what is this, x1, standardized normal data, 10 feet above, blah, blah, blah. Okay, that doesn't, I don't see any difference between those two things. 10 feet happens to be exactly one standard deviation. The fact that x1 is at 55 feet is located one standard deviation above the mean can be paraphrased by its z1 is at 1. Okay, so the point x1 is 55, but we're going to call that point 1 now. And z2, the 35, is going to be at minus 1. Okay, so one standard deviation ahead is plus 1, one standard deviation behind is minus 1, and x3, which is at 50, is going to be a half a standard deviation high, and guess where D is, x4, minus 2.342 standard deviations. X4, blah, 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 slightly higher, minus that. All right, well, where is the formula for doing this, author? I know there is one. So x4 is at minus 2.342 standard deviation. So that's because it's minus that many standard deviations. This all worked out because the numbers round off. There it is. That's the thing we're going to do. Okay, so I'm going to standardize the curve by saying my z point is going to be x minus mu divided by sigma. Okay, so if I know 1, 2, 3, 4, if I know 3 of those guys, I can calculate the 4th one. So on any particular test, we'd probably have to calculate all 4 of them one at a time, knowing the other 3. And the value of the data we have, the mean of that data, the standard deviation of that data, and what the point z is. And we do it again, and blah, 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 find the c value, blah, blah, blah. What is this going to do for me? Well, what it's going to do for me is now I can go to a table of z values and understand the probability of getting one of them without too much trouble. I'm going to do it again, going to do it again. Okay, done with that. Number 17.
Can you go to number 9 for a second? I think you messed up.
Did I mess up number 9?
Yeah.
How is that possible? That's inconceivable.
It's supposed to be 13.5 and not 3.
Oh, right there?
Yeah.
You mean I subtracted those in my head? And luckily I have red though, so I can change this to 13.5.
Come out to 20.
It does. Yeah, it does. Now I can do it in my head. I knew there's something wrong with that problem when I couldn't do it in my head. Okay. So now it's 20. All right, that better?
Yeah.
I like that better. All right. Now, how did I do that? 8 from 9 is nothing. Interesting. Interesting. Slowing down the process, though. 17. Normal distribution. Are we doing 17? What are we doing? Yeah, we're doing 17. We have a normal distribution. Mu, we don't want to use red. Mu is at 310, the mean. Q3 is at 319. Find the standardized value of these guys. To find the standardized value, I need to know mu, and I need to know x. I need to know x, I need to know mu, and I need to know the standard deviation. So I know x, I know mu, but I don't know the standard deviation. So I got to calculate the standard deviation first. 319 is equal to 310 plus 0.675 sigma. So the standard deviation, let's see, am I going to get that one right? 81 divided by 0.675. And just 390 minus 310, oh, 81, I knew it, divided by 0.675, 120. So the standard deviation is 120. That's pretty big, pretty large. That'll be good on the video, right? Me blow my nose.
It's okay,
Huh?
we've heard worse.
That's pretty good. Oh, it was worse yesterday. I think it's an allergy. I think I'm allergic to work. Alright, so what are we're trying to find the standardized value. Okay, so first problem. A Z is going to be equal to X 490 minus 310 divided by 120. Oh, that was fun. B Z is equal to 250 minus 310 over 120. C Z is equal to 220 minus 310 divided by 120. And the last one, Z is equal to 442 minus 310 divided by 120. And, okay, so I've got 180 over 120. Is that 1.5? Maybe. And then I've got minus 60 over 120, so that's minus 0.5. And then I got 90 over 100 and minus 90 over 120. What's that? Minus 0.75. And then 132 over 120. Well, when I get there, I can't do it in my head. 132 divided by 120. 1.1. Are the rest of the numbers right?
Yeah, I checked them through.
Okay. Because there's no guarantee that my maths are, well, yeah, if it's simple like that, I would better do it right. Okay. 17's done. Moving on to 19. 19. Find the standardized value of Q1 in any normal distribution. Okay, so Q1 is the mean minus 0.675 sigma. Alright, so we want the standard value of Q1. Okay, so that's going to be, I forgot already. Luckily I wrote it up there. Q1 minus the mean divided by the standard deviation. Okay, so Q1, that'd be mu minus 0.675, the standard deviation, minus, okay, so that's okay, minus mu divided by the standard deviation. Looks like it's going to be at minus 0.675 because the mu's go away and the sigmas go away, and I only have minus 675 left over. So it doesn't matter what the Q1 is, the standardization, Q1 is going to be the same, minus 0.675. Right, that was 1925. Oh, gee, you guys are going to be so disappointed if we don't make it to 9:30, I know. I'm going to have to go really slow on this one. It's going to have to take me 45 minutes. If a normal distribution has a standard deviation of 25, of 15, I'm even doing the right problem. Number 25 of 15, and a data point X at 50, and a Z at 3, what is the mean? Okay, so 3 is equal to X, which is 50, minus the mean divided by 15. All right, 3 times 15, so I got 45 is equal to 50 minus mu. The 50 goes on the other side. Minus 5 is equal to minus mu. Final answer. Mu is equal to 5. Bummer, we ran out of homework to do. That means we'll have to do the quiz next. That's the only formula that we have for the whole section is on the board. How can this be this way? Next week, the plan is to do chapter tests on the first day and final exam on the second day. I know, that's pretty silly, but that's the plan. We could all bring in our, a dozen chocolate chip cookies, and we could judge the, goodness of the chocolate chip cookie contest.
Instead of doing a final?
Huh?
Instead of doing a final?
Scott doesn't like that idea. He might lose.
Oh, I don't care.
Yeah, he doesn't care. That'd be perfectly okay.
I would rather bake than take a final exam.
I can imagine.
And I don't bake.